All right, so we're moving right along in this chapter here. 7.1 only had the one video to it. 7.2, this lesson right here, only has one video as well. And we're going to learn in this video how you deal with the sampling distribution. That was our new vocab concept from last video. The sampling distribution for a sample proportion. Remember our symbol for a sample proportion was p-hats. So what we're basically looking at is what happens to the graph of p-hats when we take lots and lots of samples. And we're going to build up some different stuff with that. There is a really useful applet here that you may want to consider looking at on your own. It's right here. This is a great website with all sorts of good statistical applets. We're going to use the one called the Reese's applets. And then I'll talk you through everything that's going on, but that link right there is probably worth following and playing along with on your own. So, what's going on for this problem right here is we have a giant candy machine for our population. So the population is a giant Reese's Pieces, one of the best candies out there, machine. And what we're looking at for this problem is what proportion of the candies in my sample, what percent are going to be orange. Orange is just the thing that I cared about in the problem. And it will let you specify over here on the side what percent of the candies are actually orange. So right now it's set to be 30% of the candy is orange. 10 is going to be my sample size, and then only one sample at a time. And let me show you how this works. So what it's going to do is it's going to spin me out a random sample of 10 candies, because that's what I set for my population size. I happen to get 3 oranges out of my 10, so my p-hat, my sample proportion, is a 30%. And then what I would do is I would go down to my nice little graph right here. I would put a dot at 30%, and I would go and pick another sample. Remember that in real life, I wouldn't have access to that info over here on the side. I wouldn't know the answer is supposed to be 30. I would just be looking at my picture down over here. So I would pick another sample. And again, I got exactly 30%, so I got another dot right there. And I would keep on sampling. That time I only got 20%, so there's a dot there, etc., etc., etc. And I picked another one, it's over here. And I would just keep repeatedly picking samples. I want to look at what happens when we do a lot of samples for a couple different scenarios here. The first thing I'm going to do is I'm going to go ahead and bump my sample size up. I was at only 10 for my sample size right there, but I want to bump it up, and I'm going to go with samples of size 50. So what it's going to do for me here is it's going to draw 50 candies at a time, which is obviously going to take a little longer. I'll turn off the animation after you see this one. So there's my 50 candies going. Oh, I regret choosing 50. There it is. So I got 26% for my sample right there. There's a dot on my picture. I'm going to turn off animation. I'm going to do it again. So there it is, 36%. And that's going to take me forever. So I'm going to jump to 10 at a time. So it's going to take 10 samples for me. And now you can see that my picture is getting populated right there. And it's keeping going right there. I'm doing 10 at a time, and I'm getting lots and lots and lots of good samples here. So here I'm already up to 102 different samples. So I have 102 people who scooped out 50 candies and found their percent of candies that were actually orange. I'm going to jump this up even further and do 100 at a time here. So there's 202, 402, 502, 602, etc. And you guys should be looking at what's happening to my picture here as I go again and again and again and just pick more samples. So I'm up to like 1,700 samples right there. And I hinted at this in our last video with that marbles example, but this graph right here does appear to look pretty normal, approximately normal in color and shape, sorry. This is the graph of p-hats, which is the proportion in our sample that were orange. So sometimes the distribution of p-hats can look normal. This is actually a really good thing for us because we've practiced a lot with the normal distribution, so we know how to handle it when it pops up. So this will be a very helpful thing. But what we need to look at next is it always normal, or could it not be? Is it just this specific, like these specific numbers right here that make it work, or is it other stuff too? So I'm going to start this over. And this time what I'm going to do is I am going to change up a few things. I'm going to change and make more of the candies orange. I meant to mention, I didn't, but the center of my picture when it was normal was right at this 0.3 right here, which was the true value. So I'm changing it to a 0.6 right now. You know what? I'm going to lower my sample size to 40. And I'm going to go back to doing, I'll just start it with 100 at a time. So it's going to throw down 100 samples right there with my new numbers. And I'm just going to keep on going. And you guys can see that, again, we are getting a fairly normal looking graph right here. As we get more and more, like you can see that it's definitely shaping up to be pretty normal. And yet again, the mean of this picture is at the actual value that I established, which in this case was a 0.6. Remember last video, we learned that an unbiased estimator has the mean equal to the real value that we set. And we set the real value at 0.6. My mean of my picture is at 0.6. So this does seem to imply that p hat is an unbiased estimator of p. If you want to figure out real p, the real percent, the sample percentage, the sample proportion p hat does a pretty good job of not being biased and centering at the value that it's supposed to. Now, this looks pretty good, and I've done two examples, which is by no means a proof, but in most situations, you're going to be okay with saying that the distribution of p hat is approximately normal. There are two kind of exceptions that I want to talk about. So I'm going to show you guys a few times when this theory kind of falls apart. The first thing I'm going to do is I'm going to call this like a 0.38. So 38% of them are orange. But I'm going to lower my sample size down to 5 candies. I'm going to turn animate back on right here because I want to show you guys what's going to happen. So now I'm only picking 5 candies at a time. That time I got 0% orange. This time I got 20% orange. Another 0, 60, 40, etc., etc. You'll see in this one, first of all, that there's a lot more spread. We're going from 0 to 60%, where the last two were a lot tighter in terms of what they allowed. We were mostly in the 50s and 70s in the last one because our sample size is lower. It's that ice cream little scooper versus big scoop analogy again. So we have more variability going on. But if I keep doing this, not only do I have more variability, let's say I did 100 of these. This picture doesn't look very normal to me, okay? This is not a normal looking picture. And there's a couple of reasons for that. The most obvious one is look at the possible options. All of my answers were either 0 or 0.2 or 0.4 or 0.6, 0.8 or 1. That's it. Because when you pick 5 candies, you can't get all those nice decimals in between. 0 out of 5 is 0. 1 out of 5 is 0.2. 2 out of 5 is 0.4. 3 out of 5, 0.6, etc. So there just aren't enough possible values here for the problem to be approximately normal. So one thing that can hold us back is if our sample size is too small. Because if it's too small, you can't have enough options here to see that full normal curve. That's one thing we got to watch out for, okay? So that is our first kind of observation. Now, how small is too small? We'll get there, but just realize that if your sample is too little, it's not going to work out. The other thing that can kind of hold us back, what I'm going to do right now is make it so 2% of the candies are going to be orange. And I'm going to give myself a nice big sample size of like 75. Okay, let's see what this does for us. So I'm just going to jump straight to doing 100 right here, and we'll see what happens. So here I go with my 100 possible samples here. I did a much bigger sample size. Before I did like 40, 50. That was cool. I jumped it all the way to 75, but I am not seeing a normal looking graph for p hat here. What I'm actually seeing is a graph that appears skewed to the right. Why is that happening? Okay, think about that. See if you can figure out, look at the numbers on the bottom here, and tell me why it should be, like why it couldn't be normal in this picture. So pause me if you need a little think time on that. The answer is my average, my center, my mean for this picture is supposed to be at 0.02, right here. That is awfully close to 0. And the thing about p is never going to be lower than 0 because it's 0%. So my center needs to go right here, but there's like a wall right here that my graph just can't cross. P and p hat are always between a 0 and a 1. So if p is right over here, real close to this edge, or this edge for that matter, of the graph, what's going to happen is my nice normal curve doesn't have room to spread out like it wants to, because it's going to get blocked by that 1 or that 0. So you end up getting a skewed picture. If p is super high, close to 1, you're going to get a skewed to the left graph for p hat. If p is super low, like we did right here, we saw something that is skewed to the right. So to summarize, before I go back to my slides, really important visuals right here. There are two things that stop p hat's graph from being approximately normal. If your sample is too small, and if p is too close to 0 or too close to 1. But that's still like not a perfect rule. It's like there's got to be some sort of a balance there. What's the cutoff, etc. And in order to get that, we'll talk about a rule that was established to kind of account for these two factors. So let me go ahead and I'm going to pull up my presentation. And then let's keep going with these notes now. So yeah, when is it okay to say that the distribution of p hats is approximately normal? N needs to be, remember little n is sample size, big enough. How big is big enough? We'll find out. But if your sample is too small, that's not going to work for us. The other thing is that p, I'm going to say real p, even though it's a little bit redundant, real p can't be too close to 0 or 1. Those are kind of the two things that stop us from having that nice normal distribution that we want to see. So what we do is we use a rule called the large counts condition. And basically what it does is it takes into account both of these factors right here. So the sampling distribution of p hats is approximately normal if you have to check two things. You need to check that n times p is greater than or equal to 10, and you need to check that n times 1 minus p is also greater than or equal to 10. It's a famous condition called the large counts. We'll see this in chapters 7, 8, 9, 10. We see it all semester long. And why does it work like this? We're not going to get into the specifics of it, but basically what this rule does is it makes sure both of these things are going to be okay. If my sample size is 5, for example, I'm going to end up doing 5 times a decimal, because p is always a decimal, and I'm not going to get 10. So if your sample is too little, well, that's not going to work out so good because you're not going to make this cutoff of 10. Similarly, if my sample is 75, like it was, that's good, but my p was so tiny, 0.02, that I didn't get over the 10 cutoff right there. If you're on the other side of things, let's say p is 99%, you would pass it right here, 75 times 99%, but you would fail it when you did 1 minus. So this checks both ends of the picture to make sure you're not too close to those 0 and 1 boundaries. So it's a lot to wrap your head around right there, but basically it does the checking for us. So this slide has a lot going on, and this up here says p hat. My face is in the way. So this top part right here is a p hat. And there's a lot going on that I want to break down in this slide. If you take a sample of size n, SRS, of size n, from a population of size big N with proportion p of successes, P hat is our sample proportion of successes. So the mean for P hat's graph is going to be real P. So the mean of P hat's sampling distribution, that's what this symbol means right here. Mu of P hat, mean of the sampling distribution of P hat, which is like a mouthful, a lot of words. What that is our graph where we take dots again and again from doing samples. Those graphs we've been building, like the Reese's graphs, that's a sampling distribution. So those graphs are going to have a mean at the actual value. When my mean was a 30%, when 30% of the candies were orange, well, that's where the center of my picture was, 30%. That's what this is saying right here. The standard deviation for this normal looking graph right here is going to be this formula. The standard deviation of P hat's graph is square root P times 1 minus P over N. This is our little setup, and we aren't going to justify where that comes from, but the book does talk about it. If you are curious, you can read it and see. This is our standard deviation formula. And then for standard deviation, you have to remember that 10% condition we talked about first semester. Being that we're picking candies without putting them back, or we're picking people without putting them back in surveys, we want to make sure that our sample is no more than 10% of our population. Before you can do the standard deviation, you have to check the 10% condition. And then finally, when your sample size gets bigger, the sampling distribution becomes approximately normal. You have to check the large counts, which is what we just talked about on the last slide. So this right here is important, so we can say it's normal if this condition is met. This is like information overload probably. There's a lot going on right here. You'll get better at it and more comfortable with it the more we practice it. So let's go ahead and wrap up this video. Oh, I have this slide right here. This is just summarizing what we've already talked about. Basically, you've got your population. You take samples again and again and again, and each time you get your P hat that you're looking for. You do a dot for P hat every single time. And if the conditions are met, you get that nice normal distribution for P hat's graph. You're going to have this for your standard deviation, this for your mean, and those are on your formula sheets. I'll show it to you in a later video, so you can use that. You don't have to have that memorized for the tests. Let's do a problem, and that'll wrap up our video right here. So we have a superintendent. A large school district wants to know what proportion of middle school students in her district are going to go to four-year college. And then we're supposing that we know that the answer is actually 80%. So this is kind of like that candy machine, how we actually knew what percent of candies in the machine were orange ahead of time. This is like knowing that 80% of the candies are orange, except instead of talking about that, we're talking about middle schoolers who want to go to college, four-year college. Okay? What is the probability that an SRS of size 125 will give a sample proportion within 7 percentage points of the true value? So it's when you read this problem, it's kind of like, wow, there is just so much going on right now, I don't even know what to do. Well, the first thing we're going to do is we are going to check to see if the sampling distribution for P hat is P hat's graph approximately normal. So we're going to check, actually, before I do even that, we're going to define a variable for this problem. When we talk about P, P hat, etc., we got to make sure we define a variable. I usually try to define the parameter. So I'm going to say let P equal the true proportion of middle schoolers in districts who want to go four-year university. Okay, so you define your variable. We want to look at the graph of P hats. So we want to see a nice normal picture for P hat, because that would make me really, really happy. Once things are normal, we do probability normal CDF. It's simple, but we have to get there first. So what we do, we got to make sure we don't have a nice Reese's Pieces example here to look at. We're going to use those conditions that I showed you on the last slide. So my first job is going to be to check the large counts. So I need to do n times p, and I need to do n times 1 minus p. And both of those quantities need to be greater than or equal to 10 for me to be in good shape here. So if I do n times p, my n, it's samples of size 125. So I'm going to do 125 times 0.8. And if I multiply that out, that is 100. That's totally greater than or equal to 10. Then I'm going to check this other guy, which would be 125 times 1 minus 0.8. Or if you want to, you can make it a 0.2. That's going to be 25, also greater than or equal to 10. This tells us that the p-hats graph, p-hats distribution, is approximately normal. It's important when you do these problems that you say it's approximate. It's not a perfect normal distribution, but it's really close. Okay? So the word approximate, if you forget that, does lose you credit on these kind of problems. So basically, this checked for us that we're going to have this sort of a situation right here, and not one of those skewed or weird pictures like we got earlier. Okay? The other things I need to do, I need to know, okay, I'm going to have a normal curve. So I've established, oh, I got a sweet looking normal curve here. Well, where is the mean and what is the standard deviation? Okay? So to figure out the mean, that part is really easy. The mean for p-hats graph is just the actual p, which they're saying in the problem is supposed to be 80%. So we're good. The mean is at 0.8. The standard deviation, I'm going to tab back real quick here. It's that formula right there. We have that square root, hard to see, but p1 minus p over n. But before we can do the standard deviation, we're sampling without replacement. We're not picking the same middle schooler a couple times. We have to check our 10% condition first. So we used that last chapter. We're going to use it a lot this chapter too. So before we can do the standard deviation, the 10% condition, and I apologize, I'm a little tight on space here. It's going to say 125 is less than 10% of all middle school students in the district. Now, in our district, that is totally not true. There are that's not even close to 10%. That's way more because we're a smaller school. But this is assumed to be like a giant a giant school district here. So this is a reasonable assumption in a real big school districts. Okay, so you acknowledge that the sample is less than 10% of the population. And what that'll do for us is it allows us to calculate our standard deviation. So now we're going to do our formula for the standard deviation of p-hats. And like I showed you guys, that formula goes p, square root p, 1 minus p over n. And you can just type that into the calculator. So if I do square root of 0.8, 1 minus 0.8 over n, I got 0.0358 if you round. All right, so I'm going to clear this out to give myself space to finish the problem right here. All right, but we just found the mean, we found the standard deviation. We said, hey, this graph is actually going to be normal. So what I'm going to do now is draw a better picture of a normal distribution. That was okay at first, but draw a nice looking picture right there. This is for p-hats graph. We've just established the mean is a 0.8. We just found that the standard deviation is 0.0358. And they ask us in the problem, what's the probability that our sample will be within 7 points of the true value? Well, 7 points could be up 7 points right here, which would put me at like points, I guess maybe that's too close because that's only 0.3 right here. So it could be all the way up here at 0.87, or it could be as low as a 0.73. If we're within 7 points of the true value, we're between 73 and 87%. So what we're going to do when it asks for a probability, we're just going to use normal CDF like we did first semester. That was a really useful chapter. We use it a lot second semester. And if I just set up my lower, my upper, my mean, and my standard deviation, I will go ahead and type that into my calculator here, and I'll let you guys know what I get. So we got 0.73 to 0.87, mean of 0.8, 0.0358, I got for my answer about 94.9%. Within 7 points, true value. Okay, so when we look at this problem right there, basically I would just restate for my answer. The probability that an SRS of size 125 would give a sample proportion within 7 percentage points of the true value is about 94.9%. I got a little weirded out when I did this at first because I was looking and I'm like, that's almost 95%. Why did that happen? But I noticed my standard deviation here is about 0.035. If you do 2 standard deviations, that's almost exactly 7%, which is what they asked about in the problem. So yeah, these problems are complicated and they take work, and this lesson might be a little bit overwhelming just with everything flying around and going on. Use this example as kind of a model for your notes and stuff like that when you're doing your homework. And just know that we will practice these a lot. At the end of the day, they end up being normal CDF problems, which you guys are good at. You just have to do all the other pieces before you get there. You have to talk about your conditions and that. So we will practice this and it will get better.